So let's get started. So today is all about building physical AI, and this is a co-host between Encord, which I represent, and Archetype AI, and you'll learn much more about both in a second. So welcome everyone from, I guess, most of the world. I've seen something in the chat about India already, um, and yeah, super excited to get started. Maybe one thing before we begin, we have a QA section in the chat. So if you have questions along the way, you can ask them and we'll try to accommodate them as well. Cool. So we have a really packed agenda today. So let's just jump in. It's probably appropriate to start with a quick introduction. So my name is Frederick. I'm the head of machine learning at Encord. I have been doing a lot of stuff with both multimodal AI, contrastive learning, reasoning, all these kind of topics. And I'm super excited today because I'm not the only host here. I have a co-host, and it's Nick Gillian. Nick, he is the co-founder and head of AI at Archetype AI. And before starting Archetype, he was also 10 years at Google as a machine learning engineer. I think even a head of a machine learning lead or something like that, Nick. Isn't that right?
Mm-hmm. Yeah.
Yeah. So we are extremely pleasant to have you here, Nick. So a warm welcome. And I don't know if you want to give a couple of words on yourself before we sort of really dive in.
Sure. I mean, maybe I'll say 2 seconds about myself, and then we can talk a little bit more about Archetype in a moment. But yeah, it's great to be here. As you mentioned, I am one of the co-founders of Archetype. I've been working in machine learning since 2006, so well before it was cool. I did my PhD back in the UK in machine learning for real-time sensors, and then I was at MIT for a few years as a postdoc doing, AI for really large sensor networks, across an entire building or, like these type of skills. And I was a researcher at Thomson for a while. And then, as you mentioned, I was at Google for nearly 10 years, where I was leading a lot of the machine learning in one of Google's hardware research labs called ATAP. And, we did a lot of very cool stuff there, both on the research side, but then also we brought a lot of new technology and new models into production as well. So yeah, I've been working on machine learning for a while. I'm, really excited about where this physical AI stuff is going, because it's really been myself and my co-founders. We've been working on it for almost 2 decades now. So it's nice to see like everyone going in this direction.
Yes, I could imagine. So we are dealing with a true expert in this case. It's fantastic. Again, very nice to have you here. Yeah, I'm super excited about this webinar. I mean, so we had this little discussion before the webinar, and I really had to constrain myself in my questions. So maybe I get to ask some of them here today.
Cool.
Yeah. So we have a packed agenda today. We're gonna give some short introductions on who we are at Encord, who Archetype AI is, excuse me, and we're gonna have a discussion about what is physical AI actually, because there's this sort of sometimes it's a bit of I would say too narrow scope in people's minds. Then we're going to talk about some of the challenges of building physical AI before showing some of the use cases and demos of what both of us are actually doing in practice. So let's begin with Encord. So Encord, for those of you who don't know, Encord, we are a data development platform. And so what does that even mean? Well, we provide everything from management and curation of all your different types of data to sending it through to human annotations, and also doing model evaluation against your data. So as a function of your data, when is my model failing and when is it is doing well? And on top of that, there's a bunch of different automations that you can do, and we'll see some of them today. And while not being the main attraction here, we will actually see Encord and how it fits physical AI's use cases. But the main attraction really today is what you guys are building at Archetype, Nick. And so if you want to give an introduction as well, that would be fantastic. So let me know when I need to change slides, and I'll.
Sure, that'd be great. And we can, I'll give a high-level introduction here, and we can maybe go into a few use cases later. So yeah, as I mentioned, I'm one of the co-founders of Archetype, along with 4 of my other co-founders, and we all worked at Google together for a long time. And the company has been operational now for just over a year, since early 2024. And really, at Archetype, we are a physical AI company, and our goal is to help humanity make sense of the world. So really, any case where you have some form of sensor in the world and you have a customer or a developer that wants to understand, reason, and then act on that sensor data in some form, right? So if we go to the next slide, physical AI is, kind of a hot topic right now, and it's really exciting to be here to talk with you and, see people from all around the world on the call. It's kind of got hot recently. Jensen has brought it up in his keynote, but we at Archetype have been working on physical AI, of course, since we founded the company. But like I mentioned, myself and my colleagues have really been working in this area of machine learning and AI for real-time sensors for a long time, for multiple decades now at this point. And we've shipped over, 15 products in this area that use things like radars or time series sensors or cameras and all of these things together, right? So if we go to the next slide, there's a big focus today about physical AI being focused on things like self-driving cars and automation and robotics. And while those are key areas, we are actually looking much broader than this when we talk about physical AI. So we really mean any use case where there's a sensor in the world and you want to make sense of it. So think of the huge industrial, factories that have thousands of sensors in every machine, for example, or an entire wind farm, which each windmill in the wind farm might have 50 sensors in it, for example, right? Or think about the entire electrical grid, like all of these use cases. If we go to the next slide, there's other areas where you may want to take at the scope, for example, of a city. You might want to take in all of the cameras across the city and fuse them with other types of low bandwidth sensors to get this macro view on what's happening across your city. And that allows the city managers and people in the state to actually both optimize this and then make sure that key use cases like safety, for example, are improved. And then if we go to the third slide, we can also think not just on this macro scale, the scale of a city, but on the micro scale of your body, for example, right? Think of all the sensors that each of us wear day to day or have in our pockets, right? Being able to take all of this sensor data and really push forward what we can do with this, as opposed to the traditional approaches where for every single use case, you're building a custom machine learning algorithm and it takes many years to develop it and ship it. We're really now in the era of, foundation models and AI, where we can have these very large models that work across many, many use cases. And we're seeing this huge velocity now in what we can do with this. So this is really what we're doing at Archetype. We're trying to take in all of these different sensor types. And if we go to the next slide, combine them together to make sense of it. And really the product that we're building is what we call Newton. And Newton is an AI platform that allows developers and companies to make sense of their sensor data through this core foundation model, which can take in many different types of sensors and then can be applied to many downstream tasks. And we'll show some examples of this, and talk about this in a lot more depth throughout the rest of the webinar. So, for example, you can imagine the more common sensors that people are used to: cameras, microphones, things like time series sensors, actuators, and robots, all of these type of things. But we're also looking at, very rare sensors that maybe are only in a specific factory, for example, right? Or the sensors that are deeply hidden inside your car to kind of measure all the telemetry and all of these things. We're building Newton so that customers can take all of these sensors and for the first time actually fuse them in one single model, and then actually use this for many downstream use cases depending on what they need. And that could be in robotics, it could be in automation, it could be in healthcare, it could be in industry, it could be in safety, it could be security, and so on and so forth. And really the big goal of Archetype is to make this platform so that it makes it as easy for any software engineer to be an AI expert with sensors as they can do today with, for example, databases and web technology and everything else. We want to bring that forward for sensors too.
So can I pause you a second here?
Yeah, please.
So from this figure, it seems so it's very clear that it's multimodal in, right? You have cameras, you have time series, all these different things you mentioned.
Yeah.
But also on the right hand side, there seem to be many different things coming out of that system. Can you maybe just elaborate a little bit on that and sort of?
That's a great point. And we'll show an example now in a second where you know, if for LLMs and VLMs today, most people are still thinking in like, you know, you put a bunch of sensors in and you get text out, you get a summary of your video, or you get a document or something. And while that's still useful for physical AI, we see a much broader multimodal output space from our customers. So for example, people wanting to be able to actually have the model directly output a control signal, this continuous control signal that you can hook up to a robot, for example, right? Or that you want to be able to actually take in a bunch of noisy sensor data and transform it into kind of a cleaned version of that, you know, virtual sensor and things like this here, right? So if we go to the next slide, I think we have an example of what we're looking at. So at the core of the model, what we're trying to do is build this physically accurate interpretation of the world. And that's basically understanding the kind of sensors themselves, and then merge this and map this with a human semantic interpretation of the world. And very importantly, be able to move between these two worlds, and then allow us to actually output, as you mentioned, not just text, but actually control signals, or these physically accurate representations of the world, or being able to kind of move across to kind of more direct semantic interpretations of that sensor data. So let me show you just a couple of examples so this is clear. So if we go to the next slide, let's look at the first one, which is this physically accurate interpretation. So if we go to the next slide, you can see here in this rig, so we've trained Newton with, you know, hundreds of millions of different types of sensor examples. And what this allows us to do is to take this mechanical system, for instance. So here we basically have a weight on a spring. It's a very simple mechanical system, and it has an accelerometer on the bottom of this. And if you could just look this video maybe as I talk over it. This is just a simple accelerometer at the bottom, and you can see the accelerometer values here in white on the screen. And what we're doing is plugging this into Newton, and we've never shown Newton this system. We have not told it it's a mechanical system. We haven't told it it's a spring, but the model is able to immediately predict this kind of very simple periodic signal, right? And this is because it's seen hundreds of millions of this type of data before in other use cases, in electrical systems, and, you know, in many different types of time series data. And the model is able now to actually take in any arbitrary time series signal and actually start to make sense of it. And you can now use this for anomaly detection or prediction or machine maintenance and so forth. So if we go to the next video, you'll see with exactly the same model and exactly the same setup, we can now take a thermodynamic system. So now we have a small temperature sensor basically in these beakers, and we can move it between kind of, you know, hot water and you know, hot system and a cold system. And again, the model is able to predict what's going to happen to the system, even though we've given it no context of what it's actually doing, right? So these are very simple examples, but they show being able to take a foundation model in the same way it's used for language or vision, and now we can apply it to all these other sensors as well, right? So if we go one step further and go to the next video, now we can start to move from the sensor world into the semantic interpretation. So if we stick again with kind of non-visual sensors, if we go to the next video, you can see now on the left in green, we have a radar sensor. So this strange green line is actually the output of the radar signal. And as you actually then see one of the folks enter the kitchen, you can now see this is how the radar sees the world. In the middle, you can see a microphone. So this is actually the output of the microphone, and there's no audio here, but there's basically a smoke alarm now is going off in the kitchen. And on the right side, you actually see the semantic output of Newton, of our model, where it's able to take these non-visual sensors. Again, there's no camera here. It's just the radar and just the microphone. And it's able to combine these together. And we've told the model that, oh, these sensors are in the kitchen. That's the only thing we tell it. And now it's able to actually say, oh, I hear a smoke alarm. It looks like there's someone in the room. You know, my recommendation is like ventilate the system and, you know, make sure the airflow is there. If there was no one in the room, the model would then say like, oh, I hear the room is empty. I hear a smoke alarm. Most likely the kitchen is on fire. Like we should trigger the system to call the fire service or something, right? So you can see that here we're able to actually get the semantic interpretation of the world through these very non-visual sensors. Again, there's no camera here, and we can still transform this to text in the same way that, you know, you would do with a camera or with other sensors.
Yeah, there's so many questions lining up here. in terms of
Cool.
how you do this matching and stuff. But I think we'll in a second we'll get
into that. Yeah. And then maybe just to finally wrap up and kind of complete the circle, we can go even further in the semantic space if we go to the next slide. So this is now looking at more common sensors like cameras. Of course, Newton supports those as well. And this is one of the key things that we'll maybe talk about in depth for physical AI is that the models need to have a very deep understanding of space, time, and context, right? They have to understand the context of, if a child is beside the railway line versus the child is on the railway line, those mean very different things, right? But for most vision models that are trained just on arbitrary YouTube data, they're not actually that good at telling these very subtle kind of spatial temporal differences. And this is one of the big things we're focusing Newton on. And we're using Encord, of course, to really help us build up this data set, these data sets to train this. So here's a very simple example where we ask the question, identify the person near the car, right? So this kind of semantic query. You can see Newton on the left, and we've actually trained Newton so it will directly output these bounding boxes as one of the multimodal outputs. So you see it, Newton has identified the people near the car, and it shows both of those. If we ask, Gemini the same query, Gemini identifies all the people and all the cars. So, it does a pretty good job of the object detection, but this kind of semantic concepts of objects near each other, it's not doing that well. And then OpenAI gives us a bounding box, which is close. I would mark that as, close enough. But again, the difference between maybe if this was at the railway station and, you have a kid who's 1 meter to the left or the right, that could be the difference between them, actually standing on the tracks or not standing on the tracks, right? So precision is important with physical AI. And then if we go to the last example here, again, another very simple example where it's like identify the ball on the books. And again, Newton is aware of like, okay, now we have a tennis ball, it's on the books, we can identify it, we can put a bounding box around it. Again, that's the output of the model directly. We're not drawing that. Gemini fails to detect anything. It just gives us a bunch of, it says books, right? And then OpenAI, for whatever reason, is saying the ball is up there in the top corner, right? So this is one of the big things we're doing with Newton, is being able to take many types of sensors, combine them in one model, and then really focus the model on the physical world to answer these very subtle kind of spatial, temporal, contextual questions.
I'm quite overwhelmed by now. It's a lot of things we can do here, both like many things in, many things out, and so it must obviously like there are so many different complications that we will get into in a second. But I think it's a really good time to sort of take a step back and look at, okay, so what is physical AI then actually, right? And so we sort of collected this quick diagram, and so what we've been talking about now is these sort of more blue highlighted things like industrial sensors or consumer devices or smart cities, while people tend to talk much more about autonomous vehicles, robotics, humanoids, these kind of things, right? Could you sort of put a few more words on like what is the distinction here, or what is the similarity?
Yeah, I mean, I think when we talk with hundreds of customers, and they cover all of these areas, and they all have very different sensors. They all have very different requirements. They work in really different industries. One is in industrial, chemical factories, and one is in security for retail stores and so forth. The thing that unites them all is they have some form of sensor in the world, and they struggle to make sense of it with the current techniques, current AI, current machine learning techniques, current signal processing techniques. And they want to be able to take that sensor data and they want to map it into some sort of meaning, right? And that meaning could be a semantic meaning. It could be a report at the end of the day that says, this is how efficient the factory was. Or it could be a real-time event that's being sent out of the system to maybe extend the traffic walk so people have more time to cross the traffic when because they have a limp or an injury. Or it could be the real-time control of a self-driving vehicle or a robot. So I think for me, all of these things fall into physical AI. Some of them are more focused on robotics and actuation. Some are more focused on kind of semantic analysis of sensor data and transforming it into a report. Some are more focused on kind of real-time alerts and control. But really, all of them they're united by the fact that there's some form of sensor, and we need to transform this into some form of meaning. That's really for me what physical AI is.
Yeah, and so your dream, now I'm speculating a bit, is that Newton will sit in the middle of all all these different problems
Yeah,
eventually.
that's our goal. Yeah.
It sounds like it needs to be a big model. We'll get into
Yeah.
that in a bit, because now we're sort of figured out, okay, so what is physical AI actually, right? It's much bigger than just autonomous vehicles or robotic arms. And so I would like to sort of try to stick a little bit to our agenda and then talk about what are some of the challenges that are sort of inherent to these physical AI problems. Um, and so we've listed a bunch here, and maybe just starting from the top left. So data is massive, right? You told me this anecdote about multiple years of data, many sensors, all collected and completely unstructured,
Mm-hmm.
right? That's
Yeah.
I think that's kind of the typical situation.
Yeah. Yeah. And for me, one of the things that's exciting about expanding beyond robotics and other areas is, for most customers and companies, they've had sensors in the world for years. Literally, some of them have had it for decades because of IoT and previous waves of industrial 4.0 and so forth. So some of these companies are coming to us with literally 4 or 5 years of data across a fleet of hundreds or thousands of sensors, and it's completely unstructured. There's no labels. The data synchronization is terrible. Part of the data was recorded with configuration A, and part of it was recorded with configuration B. And of course, in the real world, sensors break, they get damaged, they get occluded, they get dropped, all of this stuff. So there's just so much complexity here with working with real world sensing data, particularly when it's archived, and you may literally have terabytes or petabytes of data with no metadata in it or no labels, and it all has to be cleaned, it all has to be labeled, it all has to be formatted, so like these large models can kind of consume it, right?
Yeah, and it's multimodal with a capital M, right?
Yeah.
It's
Yeah.
not just like when we think about videos and images and text or audio, it's like really multimodal.
Yeah.
Um,
Yeah,
it's
and the big thing we see is both multimodal, where you have a camera and a radar and a microphone and everything else, but we also see a lot of multi-instance examples as well. When maybe there's 4 cameras and they're all pointing in different directions, right? And maybe one of them is an IR camera, and one of them is an RGB camera, and one of them is a depth camera, and like so you have all of these different versions, and then with that you have a temperature sensor, and you have the amount of pressure on the accelerator, in a car, for example, and you have all of these like non-visual sensors as well that need to be mapped into it. And yeah, we see a lot of these cases where it's really multimodal, all caps.
yeah. Yeah, so it must also be a big challenge, for instance, to how do I evaluate my system in the first place, right? Because how do I know that this sensor from this BMW is not exactly the same, and it was actually run on the same test track somewhere where we
Yeah.
recorded the data, and like there are so many things that could go wrong in the evaluation as well.
Yeah, yeah, yeah. This is actually one of the things we're starting to use Newton for. Now it's seen so much data. One of the things we actually use it for is this type of thing where we can look at the data now and actually be like, oh, this sensor is completely different than all the other sensors. Like it looks different than all the other sensors you've given me. Are you sure the sensor's not upside down, or it's a completely different model of sensor, or actually you've accidentally, there's a human error here and someone has put this recording in the wrong bucket, and because of that it's getting polluted and so forth. So we've actually seen enough data now with Newton that Newton automatically will give us these outliers and be like, this is strange, right?
Yeah. And then there's like the second row here, and I put them next to each other because they're kind of intertwined somehow, which is all these sensors, they're operating on the edge, right? So one thing
Mm,
is just like, how do you collect the data? Something might live in the cloud, something might live in some warehouse somewhere. How do you run inference even?
yeah.
It must be an extremely hard problem.
Yeah, this is a big problem, and part of this is just building a lot of good data connectors and a lot of good abstractions on the data to kind of pull it in all to one place. One of the things we're really trying to achieve with the Newton product is the ability to take uh, lots of this heterogeneous data, pull it into one model, fine tune the model, evaluate the model offline to make sure, it's performing as you need for your use case. But then most importantly, being able to deploy this back in the real world again. And this is where the inference is key here, because now you have to take these giant models and you have to run them in real time, either on the cloud on the edge or on device. And for many customers, like the breadth of the requirements and the compute constraints they have is so vast that, you know, being able to satisfy all of these is really a non-trivial problem. And even honestly, just managing, you know, hundreds of sensors in production, just that alone is, you know, a very large, daunting task, right? For encryption and security, and make sure they're all in the same firmware version, and, you know, all of this stuff, right? It's quite a bit of work to, once you've got the model to work, to actually then deploy it back in the physical world. And this is one of the things we're trying to really simplify with, you know, the work we're doing at Archetype, to really accelerate physical AI coming back into the real world again.
Yeah. It's just running inference on these devices must be an extremely hard problem, but maybe it's a topic for another day. I think the last thing I just want to touch upon here, because I think point 6 here is like, the real world is really you know, complex, and you just mentioned security is probably a big concern as well, which it is for you know, many of our customers, and also like, I guess the AI industry in general. But really point 5 here about, there's this thing about, you know, the temporal aspect, and like really understanding the real world. You said that it's like understanding relations and context and temporal things. How do you you know, take the additional step, or like do the extra thing to make Newton better than, you know, just doing the under the arm kind of solution?
Yeah, well, I mean, a key part of this is explicitly training it on spatial, temporal, contextual problem sets, right? And honestly, that's one of the reasons that, you know, we're using the Encord system, because it's very good at, for example, at labeling temporal data, right? Like, you can actually take an entire sequence of data and look at that video, or look at the, you know, audio waveform and so forth, and say, this causal system of, you know, 5 seconds or 10 seconds of events leads up to this very important event at the end, and I'm going to put the label on. But the model needs to see the whole thing. It can't just look at the final frame. It has to look at that transition, or it has to understand that, you know, maybe like a knife, for example, in a kitchen contextually means something very different to a knife in a cinema or a shopping mall, right? These are same objects, same object detector, but contextually very different things, right? So being able to explicitly train the model on these type of spatial problems or temporal problems or contextual problems is like one of the key things we're really driving our data sets and our evaluation sets and, you know, our model strategies and things towards.
Yeah, it makes a lot of sense. It just needs to see a lot of the things you're trying to solve. That's
right,
the key part.
Yeah.
Okay, so I think let's take the first row and maybe jump into a particular example of yours. So I'm gonna switch to the slide, and then I'm gonna let you sort of draw the pitch here.
Yeah, sure. This is a great example of, you know, customers who have many years of data coming to us, and they really want to try and make sense of this, because they typically have humans go through this data today and analyze it, you know, frame by frame, video by frame, video. And we're literally talking about 4 years of data from 27 plus cameras. It's like 14,000 videos, and each video might be 3 days long, across like this construction site, which is constantly evolving. And construction in the real world is one of these, you know, going back to this complexity of working with the real world. Construction is a great example of this, because every day the same construction site is changing and evolving by the very nature of like they're building stuff there, right? So an area, for example, of the construction site that yesterday used to be clean and safe is now a danger area, because, you know, you've moved out on the bridge a little bit further, or you've gone up another story, or you removed the safety netting, or, like, you know, there's now large pylons on the floor that anyone can fall and get impaled on and so forth, right? So really the goal here is to take in all of this data and train Newton to understand these type of very complex you know, river dredging operations, and then extract from this the kind of productivity of the teams that are actually, you know, in this case, widening the river for the customer, right? So if we go to the next slide, you know, there's a few really hard problems we had to solve with Newton on this one. The first one is being able to teach just Newton to understand these kind of contextually complex scenarios, where now you have, in the bottom right, you have an excavator, which is on a barge in a river, right? And this thing in yellow on the right-hand side of the image, that's an excavator. You can see the excavator bucket, you know, at the end of it. But this thing in the middle, that's not an excavator. That's a crane, right? These are very different things. The company wanted very different kind of productivity analysis for these different types of teams. So if you give this type of data to most computer vision models today or most AI models, either they won't be able to detect things at all, or they'll just say everything is an excavator, or they won't be able to understand the concept of an excavator on a barge on the river. And this is a great example where just to get the object detection to work here, you know, it was quite a bit of work. But one of the things that we have to do then beyond that is actually understand the actions of the excavator. Like, is the excavator stationary, which means it's not moving? Is it actually being moved around the river, which means like it's getting ready for work? Or is it actually dredging the river and actually excavating the river, right? In which case, that's where you should start to measure the productivity. So that's a great example of being able to understand time, because without looking at that temporal sequence and without being able to see the excavator arm is now under the water, but it's actually moving under the water as opposed to stationary under the water. Like, these are very subtle things to get to work. And this is actually one of the things we used Encord a lot for, is to take all of this type of data and then very quickly be able to go through and label like key elements of the data set. In this case, you know, excavators on barges, to help Newton understand what an excavator on a barge means. So, you know, here we can ask Newton the type of query like localize all, and then we can say like barges and excavators in the picture and build the building blocks around them. And Newton now outputs these bounding boxes to tell us, oh, I see an excavator and it's right here. So we can like trust the output of the model, right? And if we go to the next slide, you can then see how we build on top of this, which is, because we're not building Newton from scratch every time, it's a foundation model and we keep adding things on top of it. We can now take this very difficult scenario where like you have snow and rain on the camera, right? So it's occluded, it's at night. You can see the excavator here is in the top corner and Newton is correctly detecting it and tracking it. And now we can actually ask the model, you know, what the productivity was low, like explain why. And Newton is able to say things like, you know, well, given the presence of snow on the ground and the construction equipment, it seems like the weather conditions might not have been ideal for construction work, right? So this is a great example of like the power of the foundation model, because while we've taught it to understand excavators on barges in these motions, we didn't have to tell it anything about construction. We didn't have to tell it anything about snow. We didn't have to tell it about anything about, you know, the correlation between weather and, you know, productivity in a construction site. It already knows all of that from all the pre-training we've done. So kind of out of the box, the model is able to kind of reason about why the productivity may have been low for this specific example.
So like taking a step back here, to get this working, it was mostly a problem of getting the object detection working. And then the rest of the system was kind of, it was just inherent from the pre-training. So it was mostly a matter of, you know, collecting video annotations for excavators, for instance.
Yes, I would break this into maybe 3 big buckets. So the first one is, there is a lot of work to be done on just pre-processing this data to get it in the right format. So we could get the data synchronized, so the multiple cameras looking at the same object, for example, and then we pull in all other sensors like the weather, the river height, like the specific spatial location of like what part of the site this camera is looking at right now and so forth. Getting all of that synchronized in a one coherent format and like trusting the timestamps of the videos and stuff was just a huge effort on itself, because I mean there's 14,000 videos here, you know, each video is several terabytes, several gigabytes in size, right? It's a huge data set. The next big problem was then understanding the activity of the excavator. So that's what you said. It's like understanding the object detection of excavators and then the temporal action of the excavator. Like, is the excavator just being moved and towed, or is the excavator actually digging? You know, is the barge team moving the large tugboats right now, or are they just, you know, going back to the base? Like, understanding these kind of very complex temporal actions. And for that, you have to understand time well, right? You can't just look at a single frame for that. And then the third big thing, which if you go to the next slide, we can show an example of this, is what really the construction company wanted here is they want to go from sensor data to an actual productivity report, right? They don't want bounding boxes. They don't want like little animations and videos. Those are helpful to debug it. What they actually want is, here's 4 years of data. Please analyze this for us and give us a productivity report so we can start to see these trends, right? So what we were able to do now with Newton is we can take Newton and we can use it to automatically analyze all of this data and actually start to output these kind of Gantt-like chart outputs to say how effective was the team on a given date or a given part of the site. And you can now start to see these productivity reports. And here's a great example of, sensor fusion over many cameras, pulling in the weather information, pulling in the river height information, and really using this to take in all of this very complex thing, which would take thousands of hours for a human to go through and build these kind of productivity reports. Now we can do this with Newton in seconds, right? And then we can do things like in the top corner here, you can see overall looking at macro patterns, like why was this particular like day or activity either low productivity or high productivity, and they can then start to build those insights and pull those forward into future construction projects and so forth.
Yeah. So this is really a testament to also what we see quite a lot on, for instance, like regular LLMs, right? It's one thing is providing these foundation models, but you also need to have a really good application layer on top of it.
Exactly.
In order to actually start adding a lot of value. I think this is a very good example of that, indeed. Cool. Okay, now that we have sort of seen some of the solutions, some of the problems, I think it would be good to maybe take a step back and think about how, like, what this data collection actually might look like. Because I'm sure that whenever, like, if I came with my own excavator problem to you, I probably couldn't just give you my 6 terabytes of data and then we would be on. We kind of heard that you need to collect more data, you need to do something. But the nice thing about these foundation models is similar to if I'm building a legal document LLM of some sort, you need less data, but it just needs to be of a very high quality. Or just, I think that's quoted. And I think it's a good time to actually take some time to look at how you can build that. So we at Encord, we are like a leading data management platform for multimodal AI, and we know that you have, like, there are so many problems that have to be solved at once, and if the data is scattered around many systems, a lot of stuff just gets lost in translation, and it can be really hard to scale to the appropriate sizes. So what we build is really a tool where we try to bring it all together into one place. So I don't think I have to mention that if your data is scattered around buckets, you just hook in all your cloud buckets to our system, and then it'll live in like one coherent place. And so some of the things that are, I think, really relevant for physical AI is both there's this option to actually search and explore your data and index it based on if you have metadata. You mentioned sometimes it doesn't. Then you might need to do stuff like embedding searches or other sort of heuristics or tricks to find the right data for a particular problem. You can do that within our system. And there's also a big cleaning and curation part where you need to detect the outliers or detect the sensors that are wrong, or in other ways, just make sure that you're operating on high quality data. And then finally, we have a lot of automation that we can employ to make things faster. And so that's some of the things I want to show here, approaching the end of the webinar. And I think it is everything I'm going to show you can essentially do with the SDK as well. So you can automate everything that I'm going to show that I'm doing manually right now, except from bringing the human in the loop, where it's typically you don't want to automate it. You want to have the human do essential parts of the workflow.
Okay. Maybe I can add one thing here, which is for physical AI, particularly, these tools are really important because when you have sensors in the real world, which are on 24/7, most of the data you get from the sensor is not that interesting, right? Most of the time, there's no one in front of the sensor. It's just looking at an empty car park or a construction site at 3 a.m. and there's not that much happening. So the ability to kind of search and cluster and be able to actually find those really important pieces of information and label those and pull those into the model, like that's critical to be able to build really good physical AI systems. And this is why we're excited about some of the things, these tools that you're building at Encord, because it allows us to really quickly find either broken sensors or like those really high quality data samples, and then put the effort into labeling those, not the whole data set, right?
Yeah. It's something we see a lot, that like, and we even advise people or our customers to do, right? You should onboard much more data than you expect to use, because you want to select the right thing and the high impact data from all your data. And so some of the things I want to demonstrate today is I want to think a little bit about this excavator problem, but I didn't have an excavator data set, so I'm going to do it on autonomous vehicles, or well, on driving, at least on dash cams. And I'm going to show some of the tools you can employ to make annotation really fast. Then I'm going to show also how you could build data pipelines in a way where you employ automation when you can and employ humans when you should. That's the purpose. And then I'm going to show you that it's very flexible what you can actually collect in terms of data. Now, so the imaginary setup here is that I'm coming to you guys, and now I want to use Newton, and I want to have Newton be able to reason about me driving. So hopefully it's going to use some of my sensors, but it's also going to use a dash cam, and it's going to be able to detect multiple different things along the way while it's driving. And so I really want to build this fine-tuning data set for physical AI where I can sort of ground instructions. So if I'm telling the model to keep an eye on the pedestrians, I wanted to understand what that means. And if I say keep an eye on the closest pedestrian, then that's what I'm going to sort of teach it how to do with human annotations. So that's sort of the setup. So I think I mentioned this with that, like, there are a lot of problems when you're doing these multimodal things, that in many cases we see that, you know, data is separated across a lot of different tools because one tool just doesn't capture it all. And it can often be hard to bring in the humans when you need to. And finally, automation is one of these things that actually allow you to scale things. Okay, so that's the lineup. And now I'm gonna see if I can share another tab here. There we go. So first of all, I mentioned that you can build these automation and data pipelines. And one of the things I wanted to show was these workflows. So a workflow is essentially the definition of the life cycle of a piece of data. So every piece of data will go in here from the left. Then in this case, just one thought of example here. Every time it reaches a red node, it means that it's something that's to do with humans, and they'll be annotating. What they will be annotating, we'll see in a bit. And then the piece of data, once it's annotated, it can go through other nodes. If it's a purple node, it means that it's automation. It's something that you're in control of. So you can host it in your own environment, or you can employ some of the off-the-shelf things. And then, so it can do different things. Here it's just routing in one direction here for a human review. In this particular example, it could be, let's say I'm captioning videos and I need more diversity in my captions. So one thing I could do is just, you know, turn down the temperature of an LLM and ask it for more captions. But I probably don't want to do that completely blindly, but it's still faster and more, I guess, creative than if I had a human actually write 3 more captions. So I could do that, and then I can just send it for a review where I can leverage the fact that humans can use hotkeys very quickly and just read and verify and just reject everything that's not good, because then they can produce a lot and verify a lot much faster than they can type new captions. So these workflows, they are very composable. So maybe I need some sort of consensus where I need to have multiple people looking at the same piece of data, or maybe I need to route something in different directions, or maybe I need another agent to, you know, store the data afterwards. Maybe it just needs to, you know, send the data to my database once it's done with the entire process. All these things can be orchestrated in here. Right. So once you've done that, you also need to specify what is the data we're actually collecting. And that's where we use our ontologies. And so these ontologies can comprise a lot of different things. Some of the things are in relation to vision or audio or these types of modalities where you sort of have a either a temporal or a spatial relation or spatial piece of information that you need to annotate. That could be bounding boxes as we've seen now, or it could be segments in a piece of audio. It can also be many other things. And we also have various complex ways of attaching more data, even conditionally, on if the weather condition is like this, what is this and that, all these kind of things. Okay, so that's sort of how you set the ontology of like what's supposed to be labeled. Now, before you go to actually send off your data for labeling, what you can also do is this piece of indexing all the data. So in this situation, you can see that I have here a grid of all my my data. I've hooked it all into Encord, and I can very quickly browse it. And suppose I'm doing this dashcam exercise. Then the idea is that now I can very quickly select, if I care about roads where there's not much happening, then I can very quickly select some stuff that I need to be annotated. I can put it into a collection and create a data set from it. And then I can attach that data set, that particular data set, solving a particular problem into my projects. Great. So let's get to the concrete example. So in this case, I have a setup here where I want to do this dashcam annotation. So what I want to do is I want to have some automation that generates an instruction, because it can't be the same instruction every time. So I'm going to use an LLM. I'm going to have it cook up different instructions based on what's the content of the first frame of my video. And then I'm going to have annotators actually do it. Okay, so in this case, I have run a couple of tasks through the instructions selection. We can add a couple more in a bit. But then what I wanted to show you guys was the final piece of automation that you can do. So in here now, I get an instruction. I got it from that LLM. So it looked at this first image and it asked me, oh, could you please localize all cars, bus stops, and pedestrians? And so this is a query that is sort of relevant in terms of what's actually in the video. So now I can go ahead and if I need to annotate a car, I can quickly draw a bounding box, and I can leverage the fact that we have stuff like SAM included in the platform. So I can very quickly annotate very accurate annotations. I can also, if I hit Shift-T, I can also track the car. So if I need this temporal aspect, I can very quickly, so here I'll show you, now it's just tracking the car, and I'll be able to see exactly what is going on in this particular video. So this is sort of the way that you can employ a lot of different automation to remove all the hassle and all the additional overhead of all the things that do not have to happen by humans. And that really allows you to reach the scale that you really want to reach. And then finally, what I wanted to mention was that I'm speculating a bit here, Nick, but I'm guessing that you probably had to do some sort of contrastive learning, or somehow try to relate text to different modalities in order to let Newton be able to do semantic reasoning. Mm-hmm. And so one of the things we see, at least for doing retrieval tasks and also training encoders for different systems. For instance, all the sort of many multimodal LLMs, they employ Siglip or Clip or these different types of models to encode images. And one of the things you can also do is you can use this multi-tiling feature, where in this case, I've sampled a caption. So to speed up the process of getting a lot of images with their captions, I've sampled a lot of captions. And now I'm just taking the biggest database of images I can find. And then I'm here showing the top 3 recall. Because then I can very quickly just say, oh, for option 1, this is good. For option 2, it's no, it's actually not really anything, and so forth. So I can use my hotkeys very quickly to just build a data set really, really fast. And these types of multi-tiling things, they can also be used for many other things. So you can list, PDFs. Maybe it's an instruction that you have from somewhere else maybe it's a legal document if you're doing legal things. So maybe it's a manual for a machine, and you're annotating something else. So you can really compose this to your needs for the particular problem. Yeah, so I hope this gives some sort of an idea about how you take a particular problem and put it into a shape or into like a system data pipeline where you can build exactly what you need really fast. Yeah, so on that note, I'm going to jump back to the slides, and it actually concludes most of what we had planned today, Nick. Yeah, I'm very, very grateful for having you here. It's been a great pleasure and an honor to talk to you here. I don't see any questions in the QA section, so I think unless anything comes up here in the last second, I think we can actually call it a day. So thanks again, Nick. It's been a great pleasure, and best of luck with all your endeavors. I'm very, very excited to follow all of your great advancements in the future.
Thank you very much. And yeah, folks can check us out on archetypeai.io if you want to check out our website and look at our blog posts and things like this here. Yeah, and I think all these tools you're showing at the end for tracking and for multimodal annotation and stuff is exactly why we're excited to work with you guys on getting as much high quality data as we can for the physical world and really pushing these models forward. So yeah, we're very excited to see this this new wave of AI come out of the chatbot and into the real world. It's very exciting.
Yes, it is indeed. I even heard that you're easy to find on Twitter as well, right? I've heard that you have a pretty clinging name there.
We are Physical AI is our Twitter name. So yes, please reach out to us there or on LinkedIn or on any of our channels. Yeah.
Yep. All right. So thank you everyone, and see you another day.